Good morning, everyone. I'm Rich Welson. I'm the Dean of Engineering and Computing at Missouri S&T, and I'd like to welcome everyone to America's Nuclear Future. We've got a very interesting panel and a very interesting set of discussions today. I'd like to kick things off by introducing our Chancellor, Dr. Mo Dugani. Mo, over to you.
Thank you, Rich. Thank you very much. Good morning, everyone. I am so delighted to have everybody here. This is a topic that is very near and dear to my heart. As you know, when I first came on board, and I noticed that we have combined a couple of programs, nuclear engineering being one of them, I thought, you know, the future is nuclear, no question about it. Whether you're talking about fusion or fission, we must subscribe to the fact that the reliable renewable energy is nuclear. And in light of that, I am so grateful to your participation. We have a wonderful panel here that is going to guide us through our next few steps as we move forward. I'd like to mention the panel quickly. Tom Voss, our own Tom Voss. Tom is an alum of the university. He is the chair of our trustees. And Tom is a retired president and CEO of Ameren. Tom, thank you for being with us. I also like to welcome Robin Stupenhofer, Vice President of Engineering for Honeywell, Kansas City. Ben Masters. Ben, thank you for joining us. Appreciate your help in establishing our relationship with the Army Corps of Engineers. John Gall, Professor of Electrical Engineering. John, thank you for joining us as well. John is Professor of Electrical Engineering and Computer Science, I believe, at Mizzou, our larger sister campus. I would put it that way. John Wagner. John is an alum of this university and the director of Idaho National Laboratory. Very much interested in his views as well. John Warmack, who's been tireless in frankly trying to educate us, educate others. He's been on the forefront of this, if I may call it, initiative, the national level initiative that we must be engaged with. John is with us. John is the founder of Warmack and Company. I've had the delight of meeting John and speaking with him, and very much look forward to hearing his views as well. Jim Kennedy, President of 3 Consulting. Jim, thank you for joining us. John Kochak, Executive Director of Thorium Energy Alliance. So I am very, very excited. I look forward to your guidance and for us here in Missouri, frankly, we couldn't be better located for what we are hoping to accomplish. This is a wonderful science and technology university. I often refer to Missouri S&T as a crown jewel of American engineering and science education. And as you know, we are celebrating our Cisco Centennial Anniversary this year. What a better initiative. I can't imagine of a better initiative in the field of energy and sustainability, frankly, than revitalizing our nuclear engineering and radiation science program. That's our new department, as you know, radiation, nuclear engineering and radiation science. And as you know, we have a unique reactor here on campus. We invite our students, faculty from other universities, high schoolers, high school counselors, everybody to come and see what we have here. Frankly, mainly because of the fact that we want them to be aware of our program, but much more importantly, because I believe there is an education needed about nuclear energy. Let's face it, folks, there is no alternative. I mean, look, I am the greener of the greens that you can get. I fully realize that we cannot continue to pollute this planet. I fully subscribe to that. And it is in light of that I think we must revitalize nuclear engineering, nuclear energy, no matter what form of it we want. I mean, approaches are debatable. I know, for example, that John Warmack has a very strong approach to how we need to pursue this. Those we can debate, but the bigger question of that there is no alternative to the demand of energy that the world needs than nuclear. And so it's in light of that we actually devoted our very first endowed chair for nuclear engineering and radiation science. As you know, we received this transformational gift from June and Fred Kummer. A part of that is hiring 10 endowed chairs. We devoted the very first one to nuclear engineering and radiation science. And in fact, we need your help to identify the chair of this wonderful new department. So with that, I have a lot more to say, but I am much more interested in hearing what you have to say. And therefore, with that, Rich, back to you. Thank you.
Thank you very much, Chancellor Degani. So let me talk a little bit about the purpose of this session today, because there's really three topic areas we're looking to cover. The first is, why are nuclear engineers important, and why should S&T be focused on creating more nuclear engineers through our programs? The second is, what are the opportunities in radiation science, the crossover between nuclear engineering and biology and medicine? And the third, and probably the biggest one we'll talk about, is the future of nuclear energy. I had the fortune to grow up in Illinois, and Illinois went heavy nuclear just as I was going into college. And at that point in time, nuclear was viewed as the clean solution. And I would call that generation one of nuclear. And today, the state of Illinois is over 40% nuclear, the largest percentage of any state in the nation. The second phase is finding out what low probability, high impact events would have on nuclear. And so we saw events like Chernobyl and 3 Mile Island. And I think we're on the verge of entering phase 3, where we've addressed those issues and have a safe and efficient source of power. Now, I'd like to introduce our next speaker, Dr. Deji Alajo, who is the interim chair of the department, and he'll offer a few comments. Deji?
Okay. Good morning, everyone. So, my name is Deji Alajo. Most people call me Deji. My parents do, so feel free to call me Deji as well. This morning, I would be talking to you about nuclear in my backyard. In fact, this title, I think it should be more like nuclear in our backyard. That would be Niobe, something like that. But let me personalize it a little bit and say nuclear in my backyard. And in talking about this, I would go through 3 broad segments. One would be emphasizing the contribution of nuclear engineering to our society. The second one would be in the US outlook in the nuclear development and nuclear deployment coming up shortly and into the future. And then the third one is how nuclear engineering at S&T is positioning itself to be a part, in fact, a cardinal and integral part of this movement into the future. So with this, I would start next, by the way, next slide. I would be talking about 6 sectors in which nuclear engineering has played a significant role in our society. You would see on the screen here, we've got power, we've got space, defense, medicine, agriculture, and general industrial application. So I will talk about each one of these in a nutshell, which will be the crux of my first segment of this talk. So let me go on to this next slide, which will be talking about power. So nuclear power in the US, let's think of this by the numbers. There are 94 reactors in 56 different plants spread across 28 states. Next, please, next slide. I'll go ahead, quick, thank you. And can you click one more time? So to put this in perspective, we've got at least one power plant in each of those 28 states. 32 of those plants have 2 reactors. Another 3 have 3 reactors. The total energy generation in the United States in 2020, it's about 1.1 million megawatts. Now, for those that are not used to big numbers like that, I like to scale it by saying that about 20 megawatts would supply 1,000 households. So 1.1 million megawatts, and a total of 4 billion megawatt hours were generated across the entire plant. And this is irrespective of source of generation. Now, what is nuclear's contribution to that? 20% of that entire generation came from nuclear. And what is more interesting is that that 20% coming from generation just represents 9% of total capacity that we have. And how are we able to do this in nuclear engineering where generation outpaces capacity contribution? This is strictly because nuclear engineering has found ways to increase its capacity factor. Nuclear engineering operates at over 90% of its capacity factor. And so this puts us in a place where we are always consistently putting power into the grid for everyday use, saving lives. And everyone, I always like to joke that if you count 10 light bulbs in your house, 2 of them is from a nuclear source. So, and I would also mention that because we say we have 94, now it's not always been like that. Just 10 years ago, we had 104 reactors. 10 of them had been shut down through aging and other things, but still the contribution of nuclear has kept steady over all this period. So what next? So if we have this many reactors, where are they? So next slide, please. Where are these reactors? Well, one more. Thank you. So that's the picture. So you can, I like to challenge people to look at where you're from and see how close a reactor is to you. Now, I said earlier that I'm going to personalize this a little bit. So right now I'm in Rolla, Missouri. There are 4 reactors within 300 miles, 4 power reactors within 300 miles of Rolla, Missouri. Those 4 are critical to the powers to the states which they serve. One of them is Callaway Power Plant, which is just 90 miles north of us here in Rolla. Another one, we've got Clinton Power Station in Illinois. It's about 260 miles away from us. It's northeast. And we've got one south, that is Arkansas 1, which is about 270 miles south of us, and Wolf Creek Power Plant, which is about 270 miles east of us. All these are within 4-hour drives of Rolla, Missouri. So this is essentially telling you that there's nuclear in my backyard. And like I said, most of you, wherever you are in the nation, if you look at where you are, this map will tell you how close you are to a reactor that keeps giving US is energy independence as we know it. So please, next slide. So we talk about power reactors. Somewhere in the near future, which will be a few years from now, we're looking at expanding power even in the United States. And one of the directions the US is looking at is what we call small modular reactors. And small modular reactors have several many flavors. We've got many of them, but right now the ones that are near term tends to be the light water type small modular reactors. On this screen, I've shown you graphics of 2 of them, the BWRX-300 by GE Hitachi and the NuScale power reactor by NuScale. This reactor essentially leverages experiences we've gathered over the years in existing reactors and test reactors. They are designed to diversify the use of nuclear while maintaining its safety record. So we'll find that these reactors will be deployed in typical power generation. Other things we expect these reactors to do would be for process heat provision. We have seawater desalination and other industrial applications. One of the good things about this reactor is that they have really small footprints. So with such small footprints, we don't have to worry about huge cross-sectional area or they being targets. So they can become integral parts of microgrid applications, which means that they don't necessarily need to connect to the major power grid, but they could supply neighborhoods or small towns. And then you can scale them up from there up to what you need as the communities grow. So And one key thing I would say here, you might notice that some of them have like pools of water, buried pools of water. It's part of the design because these are thought of to be passively safe. In fact, the key design feature for small modular reactors is passive safety. They are designed to be walk-away safe, which means that we don't have to worry about active pumping of water if we have to keep them cool for a long time. So I would move on here to another type of reactor, which is going to come into play in the near term. Please, next slide. And that would be microreactors. Microreactors are even smaller than small modular reactors. Small modular reactors are generally classified as things that are in the order of 300 megawatts of electricity. But for microreactors, they're looking at things in the order of 20 megawatts. I said earlier that 20 megawatts would supply about 1,000 households. So with this type of reactors, one of the key features of this is that they are transportable. You can manufacture them on site, fabricate everything sealed more or less like a battery, and then you transport them to site where they need to be used. They are simple in design, and they support rapid installation, which means in a short time, maybe a matter of days or a couple of weeks, they are ready to go. Now, for this type of reactors, I've identified the kind of support they would need across disciplines. So you would find that they would need advanced manufacturing, robust instrumentation, reliable automation, and resilient supply chain. Also, one thing is the workforce implication. And so with this, I would like to conclude on power in the United States. So let us move on to another one of my favorite things. Let's go on to defense. So defense application, this is where I like to tell everybody that, do you know, or ask a question, do you know there are no gas stations in the middle of the ocean? Yes, they're not. So if you have to rely on diesel or heavy fuel oils that most vessels use, then you would have to stay close to shore and be nice to every country along the way because they would have to supply you fuel to operate. Now, the US defense, especially the Navy, runs submarine and aircraft carrier runs on nuclear power reactors. This means that they are able to go deep and wide. They can run with 25 years worth. They can work with 25 years worth of energy in that reactor stored that powers these vessels. Either it's a surface ship like the aircraft carrier or the submarines. And this is one of the things that makes the US military one of the largest in the world, and in fact, by far, arguably the strongest in the entire world. Also, another defense application is in what we call the second line of defense. Now, if you've never heard this before, second line of defense is essentially a capacity building effort. It allows us to provide defense in depth to combat nuclear smuggling or radionuclide smuggling. And so this way, we build capacity by training people, by detection, interrogation, and making sure that anything that is designated special nuclear materials, if the first line of defense, which is the facility in which those things are, is breached, they don't go beyond the borders of our nation. And this is what second line of defense is. And nuclear is critical in this strategy for national defense and security. So let me move on to the next thing, which will be nuclear medicine application. So I would like to guess that maybe some of us here have had some form of X-ray, CT scan, maybe MRI at one point in time or the other. If you haven't, it's estimated that at least half the population in the advanced world would go through one of those in their lifetime. So these are nuclear enabled technology. They're applicable to healthcare, and they've helped in saving lives, in diagnosis, and in therapy in many ways. Next slide, please. So one of the huge applications of this is in oncology, cancer treatment. So for cancer treatment, you would find something like a LINAC, which is the picture you see on here, can be used for specific treatments in cancer you can use to kill cancers, tumors, and they are very precise, they save life. And brachytherapy especially is used in treatment of things like prostate cancer, cervical cancer, breast cancer, and other form of cancers like ocular melanoma. This is one of the applications of nuclear. I would like to focus a little bit on radionuclide therapy because that is near and dear to my heart. One of the things that is treated in cancer is cancer of the liver cirrhosis. And one of the ways in which it is treated is using what we call TheraSphere. TheraSphere was actually developed by a faculty at S&T here in the 90s. It's essentially putting radioactive material inside microglass beads, and those glass are put into the site of the cancer. And it's been very effective in treating and managing that type of cancer. And so I could point to you that for everybody that benefited from that kind of treatment, they should be grateful to nuclear engineering. And by the way, I would say S&T too would like to take credit for that. And now I would move on to agricultural application for nuclear. If you went to a grocery store, there's a chance that the apple you would pick out on the table has been irradiated. Now, it's not just, it doesn't turn you to a mutant. And I actually challenge people like, oh, when you see the movies, I grew up on comic books, and comic book tells you that if you're exposed to radiation, you become Spider-Man or you become Hulk, or one of those superheroes. But we know that is not always true. It's just comic book. In real life, irradiation helps in many ways. So when we irradiate certain food, it kills microbes on them, microbes that makes them spoil real fast and reduce their shelf life. That, in doing that, the radiation helps to reduce that spoilage. In fact, it's estimated that up to 30% of food is lost to spoilage due to the action of this microbe. And this is where I would make an anecdotal reference to one of the, to an experiment that was performed by our students a few years ago, about the time I just joined S&T. It was actually trying to see shelf life of flowers and see if irradiation helps them or does not. So they had flowers and irradiated them at S&T reactor here, and to see how this flower would respond to would respond in terms of shelf life. So what they found out was that at lower levels of doses of radiation, those flowers actually lasted longer. But at a particular threshold, of course, they died faster. So this tells them that the conclusion was that the microbes that actually accelerated the wilting of this flower were killed, and that's why they had longer shelf life, because of that dose of irradiation that they were exposed to. And I thought that was a very neat experiment, and this was one of our students' Reactor Lab 2 class. This was probably in 2011 or 2012. So the other thing in agriculture, please, next slide. Agriculture application is in fertilizers. I happen to come from a family of farmers back in Nigeria, and one of the things that I know very well is fertilizers called NPK 15, 15, 15, N being nitrogen, P phosphorus, and K being potassium. It's actually good for plants. Now, how does nuclear interface with stuff like this? Turns out that research in fertilizers would like to know the uptake of those nutrients in plants. And so there are nuclear techniques for us to trace some of these elements in fertilizers, so particularly nitrogen and phosphorus. Nitrogen 15, which is stable, and phosphorus 32, which is radioactive, about 14 days half-life. And so with nuclear technique, we can actually trace the uptake in plants and see how the plant is using of the nutrient provided to them through the fertilizers. So that's one of the things that nuclear does in agriculture. Another thing in agriculture, next slide, please, is selective breeding in plants. So this is actually extensively being used in places like rice in Bangladesh and sorghum in the country of Mali, which is in Africa. So how do you do this? You take a particular seed, irradiate them, maybe gamma or neutrons, and then they would have new characteristics, and then you select the one that exhibits characteristics that you prefer becomes the one that you preserve and select. And in doing so, you have a new quality of plant that exhibits all the necessary qualities that we would prefer. Next slide, please. Agriculture, again, pest control. One of the things that a lot of environmentalists they really criticize about pest control is the use of chemicals in pest control. However, nuclear can help in this area. In fact, what we do in this area is called sterile insect technique, in which you would take pests that are disturbing crops and stuff like that. You sterilize them through nuclear methods, and then we reintroduce them into the environment, and that way you can stem procreation of this pest. And in doing so, over time, the generation would fade because the sterile ones are competing with the sterile ones are competing with the ones that are fertile. Now let me go on to industrial application of nuclear. One of the key ones here is seawater desalination. Please, one slide back, please. Seawater desalination. Thank you. So potable water may become scarce, it may become a scarce commodity someday. But the sea water is almost an infinite source of water for us from practical terms, but it is salty. With nuclear technology and nuclear techniques, we can remove the salt from this and create more potable water for people to use. And this would actually be very beneficial to places that are by the coast, but also don't have a lot of water supply. So if you're looking at places that are desert, but close to sea shores, this becomes a good technique for producing potable water in those areas. Next slide, please. Radiography inspection. So many industrial components need to be inspected either for defect or to make sure that maybe a point of coupling that is not easily visible is properly aligned. This is where radiography becomes a very good technique. And this allows us to be able to see things where otherwise we would not be able to explore through nuclear technique. I would not spend much more time on this. And one last thing I would talk about in industrial application would be well logging. I mentioned earlier that I come from a country called Nigeria, I suppose. If I have not, yes, I was originally from Nigeria. And we have huge oil. I mean, crude oil is the wealth of Nigeria. One of the techniques that is near and dear to every petroleum engineer in Nigeria is well logging, because it tells you what is subsurface. Through nuclear technique, whether it is gamma or neutron, we can tell everything that is from the surface all the way down to where the oil dwells. In fact, well logging is not restricted to just oil companies. Even water wells that we dig also can benefit from well logging technique. And these techniques are very nuclear in nature. So space application. This will be the sixth of the areas I will talk about. NASA has successfully sent several many probes to the ends of the solar system. I've listed a number of them here. You would see some of them have completed their mission and some are still ongoing. And all these things is where I would like to point out that beyond the asteroid belt, solar energy does not help you in any way. So what do we use to power this probe? They're called RTG, radiothermionic generators. They're essentially nuclear radioactive materials that produces heat, and that heat is converted to power used by these space probes. In fact, more recently, NASA had put so much effort into what we call general purpose heat sources, which use plutonium-238 to provide heat for those spacecraft. And so we see that nuclear has played so many roles in our society, either in science, in everyday life, human interest, and just health and wealth altogether. So this is where I would go to the second segment of my talk, which would be US role in all of this. So the national outlook, to my mind, is keyed into one phrase: global relevance. The US is a pioneer in nuclear technology, and we need to keep that global relevance. We need to be at the forefront of everything. So US leadership is critical to the global development of nuclear. International presence should be enabled. So this is where the United States, we need to work through all various government agencies, including departments, for example, Department of Commerce, Department of State, Homeland Security, all of them working together to secure US interests in the international space when it comes to nuclear, allow us to be able to sell our technology where needed while we're protecting our national security in the process. Also, enabling technologies. Nuclear happens to be something that supports two ways. Nuclear relies on other technology that are non-nuclear to be effective, and also nuclear supports other things that are non-nuclear to be effective. So this is a synergy between nuclear engineering and other aspects of life. So nuclear, in a way, it's a help skill set. So nuclear never stands alone. So if you're talking about enabling technologies, maybe we need instrumentation that would involve electrical and electronics and computational people. So this is critical for us to maintain our global relevance and leadership in the world. Also, economic impact. We'll be talking about things like GDP, growing GDP, talk about national impact and local economies that support all these things. So the next part of national outlook would be what I call the local strategy. So what do we do about workforce? What skill sets do we need? What skill sets are required, and at what level of education and training would we require this? Advanced manufacturing. How can we leverage advances in manufacturing to improve quality? One, reduce time to completion of a project. Two, and to reduce costs. Those three things are directly linked to wealth: quality, completion time, and cost reduction. Also, instrumentation. How do we implement things? For example, digital instrumentation, reliability within regulatory environments. That's very key, especially with everything nuclear. And also, how do we resolve issues of multiple reactor units with, say, reduced operators? Right now, we've got every unit has a set of operators. When you start going into small reactors, how do we automate this? How do we assign operators to a fleet of reactors, and what is the framework to do that? And last thing I'll mention here is supply chain issues. Everything we do, we need supply chain. For example, I would say that at the point we realized that we were losing skill sets to build reactor vessels in the United States. If we lose that kind of skill set, then it turns out that we would rely on other nations to be able to do those kind of things. So resilience of supply chain within the country is a key aspect of this. Now, let me move on now to the third part of my talk, which is now focused on S&T nuclear engineering. For us, we've identified 4 key elements. One is interdisciplinary strategies. The other one is innovative research, leadership development, and impactful solution. When we say this, for us, we look at interdisciplinary synergies in the concept of leveraging competencies on campus here to advance our nuclear engineering program and affect nuclear engineering progress in the nation and the world at large. We want to support development of future technologies in nuclear and radiation science space. And that is our key into the innovative research aspect. And leadership development, we look at it in the paradigm of students. We are training the next generation of leaders in nuclear. And we have to do this to make sure that nuclear, we continue advancing nuclear and US interest in nuclear, even to the next generation. And also directly affecting the quality of life of people in an ever-changing world. And this is why we say we need impactful solutions, things that people see and need to be immediately attributed to nuclear engineering. In light of this, let me talk about some research highlights that we have in nuclear engineering. I would talk about 6 points quickly, and then I would wrap up. Let me check. Am I doing well on time? Yes, I am. So first thing, we are developing experiment and high fidelity modeling techniques for high assay, low enriched uranium fuel systems to support small and micro reactor development. Up till now, power reactors rely on low enriched uranium fuel, LEUs. But as we move into the paradigm of small reactors and micro reactors, we need a little bit more fuel materials in them. So enrichment becomes a little bit higher. And what we call the high assay, low enriched uranium fuels are fuels that are enriched just up to 20% in uranium-235. There are experiments that need to be performed, especially in reactor physics and criticality studies, to be able to support codes that have been developed in the design of this type of reactors. A code is only as good as its power to rightfully predict stuff. So we have to benchmark a code to experiment, or we have to validate a code with experiment rather. So those validation things, we have to create them through experiment. This is why we're developing experiment. And in fact, this work is in conjunction with the Advanced Reactor Concepts Group at SMDA National Lab. And one of my students is actually working on this. The next highlight would be in the using of additive manufacturing to make silicon carbide-based materials for nuclear application. this project is actually supported through IUP, which is Integrated University Partnership Fellowship, which was granted to one of our students. Some of you may know here that silicon carbide is one of those materials that is being tapped for what we call accident-tolerant cladding for new generation fuels. And so being able to manufacture this in a different way that we've always done it and be able to characterize the properties right is integral to the success of that program. And this is the work that our student is doing along this line. The third highlight I would like to pick on is dear to my heart. That this is actually a NASA project. So in this project, we have the characterization of high temperature properties of submerged nuclear fuels for nuclear thermal propulsion. This is sponsored by NASA. In this case, NASA, especially Marshall Space Flight Center, is developing new generation of nuclear thermal propulsion systems, and they need to characterize the properties of those fuels over the long haul. The result of this research would move us a step closer to that journey that a lot of people want to make, that is to travel to Mars and colonization of Mars. So really this is the work out here. One of our students is leading that work, is doing that work right now. Then the fourth one I would like to point out here is using swift heavy ion irradiation techniques to manufacture new devices for sensing and energy harvesting application. So in this case, we are depositing certain materials on metamaterials so that they are able to sense more, especially in what we call Raman scattering. It amplifies their Raman scattering characteristics. And also one of the real life applications of this is that it can be used to enhance other sources of energy or energy harvesting applications like solar panels or hydrogen fuel cells. So this is a groundbreaking work at the scientific point, and gradually we'll move this into a place where it can become something that would advance not just nuclear alone, but also alternative renewable energy sources like solar and fuel cells. My fifth highlight would be computational fluid dynamics. So one of our students working this work is together with Oak Ridge National Lab, through DOE through Oak Ridge National Lab, in which are using computational fluid dynamics simulation to optimize design of 3D printed heat transfer components. These are components that are intended for use in tokamak type fusion devices. And so in present day, everybody, I think today 3D printers are so ubiquitous that they're all over the place. You can buy one, they're cheap now. So we can 3D print just about anything these days. So this means that a new design paradigm in which we actually model things and tweak shapes, simulate those shapes, look at, optimize the shape and the structure for certain performance characteristics, in this case, heat transfer, that I would like to achieve. And when we're done with that optimization, and we say, okay, this is the shape that needs for this component to be for us to have the best heat transfer properties for this type of application, then we can go ahead and 3D print them. Gone are the days where you make something and then characterize them and say, oh, by the way, you should not exit this point. This time around, the paradigm is turned on its head, where we actually design for a property that we like and then use that design to determine a shape that supports that property or level of application or threshold that we need. So this is one of the great things about this work, and I really love this. So for me, I think this is the way we would go with many other things going forward, being able to essentially use method to determine characteristics we want, and then we can now manufacture from there. And this ties back into additive manufacturing that we talked of in the very first place. And then the last one of these that I would highlight is in the area of passive containment cooling. I put this at the back end of things primarily because I want to circle back to the issue of new nuclear power systems like the microreactors and the small reactors, which rely on passive cooling systems. So what we're doing here is measuring things like detailed condensation heat transfer rates in a passive containment cooling system. So when you have, we try to stay away from active system primarily because active system requires external power to run it. Suppose what happened in Fukushima happens where you lose offsite power completely. We don't want to rely on offsite power to make things controllable. So this is where passive cooling through natural phenomenon becomes critical to deployment of these reactors. And oh, by the way, it is something that can be done, but we are doing the research here to make sure that those things are valid based on the combination of experiments and now develop models to predict them beyond experiments and be able to say that our models are predicting exactly what would happen in a real life scenario. So having talked about this, highlight there are many more, but I don't want to spend so much time talking about things that are going on here in terms of research. I would like to conclude by wrapping this up and saying that for nuclear engineering, we have strategic focus. And I've listed the 5 primary things we're focused on, and I would explain them to you. First thing is we say the minds at S&T. This is an acronym. It just says Multidisciplinary Institute for Nuclear Engineering and Sciences at Missouri S&T. That's what the minds at S&T means. And through this minds at S&T, we look to engage experts on campus in addressing specific and imminent challenges in nuclear engineering and nuclear technology across the nation. That's what this is all about. And that's our focus. And that's what we're doing. In fact, this is what these things tie into in the things I've highlighted so far. The second part to this is degree pathways. It's just one word. So degree pathways is that we are nuclear engineering and radiation science. So while we do radiation, while we do nuclear engineering, we're also doing radiation science. Radiation science, we tie into things like medical application, accelerators, other technologies that are not non-nuclear power in nature falls into this category. So we will create degree pathways, which means that we're looking at synergies that allows us to have hybrid type of degrees with existing programs on campus here, developing new ones, creating pathways to medical school for our students. In fact, we already started that, and I'm glad to tell you that in the past 5 years, we've had about 8 students go on to medical school. Another 3 will be going on to medical school this year. And so this is one of the things that we are focused on in nuclear engineering, to establish that multidisciplinary pathways to prepare our students for the future. The third thing is student success. All this is in vain if we do not focus on student success. For us, we need to improve our student success both at undergraduate and graduate level. This means exposing them to the right nuclear world as early as possible, sending them on internship, getting them to meet with professionals, showing them all sort of pathways and developing their interest in nuclear as they go through the program here. The fourth one, we say national reputation. One of the things that we're focused on is that we have a national reputation in that we produce very good undergraduates. We produce excellent undergraduates, but that is not the only reputation we want to have. In fact, we do cutting edge research at graduate level here. So we want that to be front and center at the nation so that people know what our students are capable of doing. I'd like to say a couple of years ago, actually 2 years ago, our students went to ANS National Conference and they swept awards there, ANS Student Annual Conference, by the way, and they swept the awards there. And that is a point of pride for us. This is a point of pride for us in nuclear engineering. And we want the world to know that. We want the nation to know that, and our colleagues everywhere to know that. And in fact, you are a stakeholder. We want you to know that, and not just think of us as a program that produces great undergraduates. By the way, great undergraduates go on to be great researchers and great scientists. The last point I want to make here is global presence. We are striving to grow a strong global nuclear engineering program. This means that we also focus on international students. We focus on international scholars. We bring them here to advance nuclear technology in the United States primarily and the world at large. So with this 5 point, I call it my 5 finger points. This is one thing that guides the new nuclear engineering and radiation science department. And so with this, I would like to close and say thank you for listening to me. And we are glad to be one of the people that want to drive and channel America's nuclear future. So at this point, I would yield to the Chancellor, to Dean Welton, to take on the rest of the program. Thank you.
Thank you very much, Deji. That was a great overview of what we're doing here at S&T. We're now going to broaden out the discussion. We have a series of 2 panels to wrap up the public session of this meeting. Each are going to run about an hour. And the way we're going to run the panels is we have 4 speakers in each. I'll introduce them. Each of them will have about 5 minutes to give an overview of their background relative to the questions that we have. And then we'll have a series of questions that we've prepared. You'll also have the opportunity to submit questions, and we'll spend the rest of the hour going through those. So far, we've seen the view of nuclear from S&T looking out. And one of the challenges that nuclear engineering has is that nuclear engineering programs tend to be small. I was actually originally a mechanical engineer, and there are hundreds of mechanical engineering programs in the nation. I spent my career in aerospace, and in aerospace engineering, there's tens of programs. In nuclear engineering, there's on the order of 20 programs across the nation. And so these programs tend to be small, they tend to be at risk, and we're making a commitment long-term to nuclear. But we want to hear from you why nuclear is important. And so the topic of this first session will be why nuclear. We have 4 panelists. The first is Tom Voss, who is retired president and CEO of Ameren. The second is Robin Stupenhofer, who is vice president of engineering, Honeywell, Kansas City National Security Campus. The third is Ben Masters, research physicist, Engineering Research and Development Center for the U.S. Army Corps of Engineers. And the fourth is John Gall, professor of electrical engineering and computer science, adjunct professor of biomedical, biological, and chemical engineering, University of Missouri. And so we're going to ask each of the panelists to spend about 5 minutes talking about their experience and their relationship to nuclear engineering. And the first will be Tom Voss. So over to you, Tom.
Okay, I had to unmute myself there. Sorry about that. As you said, my name is Tom Voss. I got a BS in electrical engineering from S&T back in 1969. Also later on got a professional degree and an honorary doctorate degree from S&T. I'm currently president of the S&T Board of Trustees, and for a few months I was a curator of the University of Missouri system. Currently I'm executive chairman of a startup company in California called Smart Wires, which makes a product that can control the flow of power on the electric grid in real time, something that has never been done before. I think the reason for was selected for this panel is because I was with Ameren for 45 years. The last 5 years I was CEO, but before that I was the chief operating officer and president and CEO of Ameren, Missouri. And of course, Ameren, Missouri owns and operates a 1,200 megawatt reactor in Callaway County in Missouri. It's been an outstanding asset for the company for a long period of time. During my term at Ameren, I also attended an MIT 4-week course on reactor technology, sponsored by the Institute of Nuclear Power Operations in MIT. And this was for non-nuclear people to understand the intricacies of owning and operating a nuclear reactor. So with that, I think that kind of sums it up.
Great. Thank you very much, Tom. Secondly, we'll have Robin Stupenhofer give her overview. I think, Robin, we need you to unmute.
Let's try that. Is that better?
There we go. Thank you.
Okay.
We lost you again, Robin.
We're not hearing you, Robin.
All right. I'm not sure where I'm muting and unmuting here.
There we
Is that
go.
better?
We can hear
Okay.
you now.
So Robin Stupenhofer, I am Vice President of Engineering at Honeywell FM&T in Kansas City, Missouri. I'm on the Nuclear Engineering Advisory Board and have a degree in mechanical engineering from the University of New Mexico. down in Albuquerque. And I guess to go back to why I'm on the panel, one, related to the board, but also we do not do a lot of nuclear engineering here in Kansas City, but we do have some areas where we hire them, but we work very closely with the national labs in New Mexico and California, so Los Alamos and Sandia National Labs in New Mexico and Livermore National Labs in California, and they have the nuclear piece of that for the nuclear weapons mission for the U.S. government. So really trying to tie production of things besides reactors into the nuclear engineering piece of that. And so that's probably about it at this point on that topic.
Great, thank you. Ben Masters?
Good morning, can you hear me?
We can.
Okay, good. Good morning, my name is Ben Masters. First of all, thank you very much for having me on the panel. I really appreciate it. Probably best if I go chronologically. I started out getting a bachelor's degree in physics at University of Illinois. And to be perfectly honest with you, I wanted to do something a little bit more applied. And a friend of mine who I met in a lab actually told me about nuclear engineering, and I started looking into it, and I decided then and there I was going to go to graduate school in nuclear engineering, which I also did here at University of Illinois. I got both my master's and my doctorate there. My master's primarily focused on plasma physics, and my doctorate focused on degradation mechanisms involving plasma material interactions for compact X-ray sources, specifically a material known as lead zirconate titanate. In the course of doing that, I came to be aware of the Construction Engineering Research Lab, which is one of 7 labs within the Engineer Research and Development Center organization, which is the research arm of the Army Corps of Engineers. So if the Army Corps of Engineers has a problem, we're the ones who try to find solutions to it. We're 7 labs spread out over 4 locations, one of which is here in Champaign. So I've been down here since 1999. And people will often tell you from this area, once you get here, it's kind of hard to leave, and that is absolutely true. And during my 13 years during my work at the Construction Engineering Research Lab, I've done work in almost every area that I can think of, and I'm sure I will. It's probably best if I don't list them because there are too many to count. But over the last 28 months, I've become involved with Project Pele, which is the Department of Defense's effort to develop a small modular mobile nuclear reactor, bringing my subject matter expertise in support of the Army Corps of Engineers. And I think the reason that I was brought onto this panel is I can help offer at least the view of what the Army might be able to benefit from in adopting nuclear power.
Great, thank you very much. And our 4th participant is John Gall. John?
Well, you know, in the context of it's a small world, let me see, make sure that I got the right one here. I want to open up this one here, see if that'll let me do that. Let's see, I want to do my desktop share. Let's see if that will come up. So do you see a PowerPoint for America's nuclear future?
We do.
Okay, great. Ben, my background is I got my PhD in tokamak plasma physics. I ended up using a lot of my career doing materials in extreme environments. And Robin, in the 80s and 90s, I was a professor of engineering at the University of New Mexico. So it's a small world that we're all in.
It is, and I graduated at 85, so.
So, you know, we were probably walking around on campus. So here we go. I'm going to talk a little bit, and I'll be fast, but, you know, I'm a college professor, so I can't hardly not have slides. But an area that a lot of you probably don't know a lot about, and so I'll go through it rapidly. You know, radiopharmacology, and people ask me, you know, well, what do you know about pharmacology? Or about 20 years ago now, I moved to Columbia to work at MER, to apply my nuclear science background to making radiopharmaceuticals. And there's lots of people that are necessary for radiopharmaceuticals, from docs to vets to biologists to chemists, but people with a background in nuclear science, nuclear engineering are absolutely critical in this area. And it is an area that is expanding rapidly. So even just 10 years ago, if you look at this chart, if you went to hospital in the United States, you had a 1 in 4 chance of getting a drug that had in it technetium 99 metastable, which is a nice gamma emitter and is used in SPECT. And it's in 10 or 15 different drugs. Stress, if you take a stress test, you're going to get technetium 99. We make and ship Moly 99, and it decays to technetium 99 at hospitals. So the Moly's got a 66-hour half-life and the technetium 6. But you know, 10 years ago, none of it was made in the United States. And this was considered to be a security issue. It was a supply chain problem as well. And so just recently, a company called North Star started producing Moly 99 for the United States, first at MER, and they continue to make it at MER in Columbia. And they are now just acquired a couple of accelerators to make that radioisotope in Wisconsin, where they're from. Interestingly, North Star is a big player now in radiopharmaceuticals in southern Wisconsin. There's another company in southern Wisconsin, Shine. There's a company called Phoenix. All of these are guys out of the nuclear engineering program in Madison who have done these startups and are making radiopharmaceuticals. So the connection is clear to radiopharmacology. The big thing that's happened recently within imaging has been PET, positron emission tomography. And in reactors, we can add neutrons to isotopes. In PET, you add a proton from an accelerator. And PET images the physicians really like a lot because they're very clear, and there's a lot of reasons for that. And there's been explosive growth in PET imaging. You need a cyclotron because they're short-lived. And so it started out, they were all in major medical facilities. There's hundreds of them now, cyclotrons, based in hospitals. There's one in Columbia. It's a private public partnership. The private part makes clinical drugs that are necessary and needed. And then the machine is available for research, materials, irradiations in support of fission reactor research, and the production of rare isotopes for the people doing science in the radiopharmacology area. So that's the landscape. And 10 years ago, therapeutics, drugs that treat cancer, was a very small slice of the pie, but that area is expanding rapidly. And here's an estimate that therapeutics will double in the next 5 years. I think that's very conservative. There's been tremendous success in therapeutics. And I have been privileged to do research in this area, and we'll talk very quickly about it here in a second, for a drug that is called Quadramed. It uses an isotope of lanthanide, samarium. It's indicated for people with a particular cancer. Personally, that my mother had when she died 35 years ago. So it's a fantastic area. It's really an area where you can do research, and it makes you feel good at the end of the day. Here is some of the stuff that's going on, and try to close my picture so we can see some of this. North Star is that startup out of Wisconsin, now making the only company that's making this really essential Moly 99 in the US. Iodine 131 is a cure for thyroid cancer. It is the only cure. Boston Scientific and TheraSphere produced in Rolla, Missouri. And I'll talk very briefly about that. Quadramed, the drug that I work on. And you can see for the nuclear engineers in the audience, BWXT. There's a BWXT radiopharmaceutical division. They are getting into the Moly-99 business. They're going to make Moly-99 in Colombia with MER, but they're also going to use other reactors in Canada, I think, largely. So, you know, there's, I'll tell you, I have a friend who is works in the radiopharmaceutical division of BWXT, who is a graduate of the S&T nuclear engineering program. And they need nuclear engineers to make radiopharmaceuticals. And here, this Lutathera, and I'll talk briefly about that, is the one that is really so energizing the industry right now. Okay, here's the Rolla connection. MOSI, Delbert Day, Curators Professor Emeriti, started this company to make glass beads. They're like the finest sand you've ever held in your hand. They have yttrium inside of them. They come to Columbia where they're irradiated. BWXT dispenses them, and Boston Scientific owns the material. 70,000 people have been treated for liver cancer with this modality. And it's so far been used only as a humanitarian device exemption, which means there has to be a committee meeting and all of this stuff. It's still with all of the red tape that is required to use an experimental drug. 70,000 people have used it. Just now, it's been approved by FDA, as many drugs are now being approved in a number of radiopharmaceuticals. It is really an extraordinary sea change in the use of radiopharmaceuticals in medicine. There's the Moly, decays to technetium. 16 million people a year use that. And so is a very important thing that we have access to that drug. BWXT now in that business with Northstar Nuclear Engineering, providing those radioisotopes. What's going on in radiopharmacology now are these, let's say, guided missiles. These drugs, that molecule down there in the lower right-hand corner, dotatate, that will preferentially go to tumor cells and cancer cells and spare healthy cells. It tricks the tumor cell into believing it's a hormone that the tumor cell is looking for. These receptors are overly expressed, as they say, on tumor cells. They go and lock in. The tumor cell is tricked into bringing that inside of the tumor cell. And in this particular case, lutetium-177, which is a beta emitter, decays inside of the tumor and destroys the tumor. This was approved perhaps 2 years ago. Neuroendocrine tumors, you might know it as pancreatic cancer. This is the cancer that killed Steve Jobs. Huge demand for this drug now. It's a therapy that works where there is really not much in the way of anything else that does work. Coming online very soon, we believe, after this, utilizing lutetium-177, different drugs aimed at prostate cancer and then breast cancer. Really promising time, and the production of these isotopes now are increasing dramatically. And here's a cyclotron. This is a cyclotron that we have. This is a private-public partnership. This machine produces very short-lived PET isotopes. The one that's used a lot is fluorine-18 and FDG. That's a sugar, fluorinated dioxyglucose. If you looks like you might have cancer, they'll inject this into you. The sugar goes to the high metabolism, which is the cancer. The physician has a beautiful picture of both the PET scan fused with MRI, so that she has all of the anatomy and she can see where the cancer is in the body. So that drug is used extensively now. And nitrogen-13 is a 10-minute half-life used in ammonia for stress tests. And this is why it's showing up, cyclotrons are showing up at hospitals all over the country because of the short half-life, and a real opportunity actually for educational groups or universities in the near neighborhood to utilize these machines for basic research, everything from materials research to isotope production. Okay, so all of this, I'm done now, but this center, this $250 million system building, Next Gen Precision Health, one of the major initiatives in that building is going to be cancer research, and a major component of that for the system is going to be radiopharmacology. And I look forward to utilizing the resources within this building, and it's a very exciting time. And I'm done. Thank you.
Thanks very much, John. So now we're going to go into 4 different areas specifically, and keep in mind the question we're trying to answer is why nuclear? And so in the first case, we're going to talk about nuclear engineering as a discipline, and why is it important for us to not only have a nuclear engineering department, but also to continue graduating students at the undergraduate and graduate level in the discipline of nuclear engineering. And so the question I'm going to ask is, why is nuclear engineering fundamentally important to the nation? And the way we'll work it is we have 4 panelists. Just jump in. You don't have to raise your hand. Let's hear your thoughts on that topic.
Well, I'll start. This is Tom Voss. I know Ameren has a nuclear power plant in Callaway County, and we probably have 900 or so workers there. I'm not sure how many are engineers, but there's several hundred at least. And we always need a good source of employees. And the fact that Callaway's in a remote area and the schools are close by in a remote area, it helps supply the talent that we need to operate a plant like that. So it's very important for both Columbia and Rolla to continue to produce good nuclear engineers.
Great, thank you.
This is Robin. I will jump in from the national defense posture position. So we have a stockpile that is the deterrent. It's important that it stays viable and robust. And with that, there's continuing research that goes on to make sure that the existing nuclear portions of those weapons are maintained viable, the research, all of the pieces that go into making a weapon strong are critically important as we move forward. Treaties have prevented the production of new pits over time. There's a vision of being able to produce pits in the future, so understanding where we can get those nuclear engineering graduates into the business at either the bachelor's, master's, or PhD level is going to be huge as we move into the next generations of weapons and what's out there. So big deal that we have them. We've got the mechanical aspects of it that really lead into the nuclear pieces. So as we go forward, it's going to be important that we have a pipeline of folks who are interested in working in the defense area and not just in reactors, which is, I think, one of the main pipelines that Missouri S&T has. The other piece that I've seen used, and this comes from my time on the board, is through the national measurement areas and making sure that we've got a lot of standards and a lot of things that apply to the nuclear side. We use standards across the board to drive our business. So that's my input.
Thank you. Ben, could you give a DoD perspective?
Since we're going in order, yeah, might as well. I think one of the most important things for the DoD is resilience. Is just ensuring that there is always an ample, stable power that is available. But I also want to mention from the academic side, being a more recent graduate of a nuclear engineering program. I think we're taught to think differently than the rest of the engineering disciplines. Just a quick anecdotal story. A couple of years after I was hired, I was talking with my supervisor, and I said, just out of curiosity, was there anything that you saw specifically so I can continue to play that up. And without skipping a beat, she responded, because you thought differently. And I think that's something that is inherent to nuclear. It's a philosophy. It's a problem-solving approach that I don't think, and I don't mean to bash the other disciplines, but I don't think they have that as much. In part because nuclear touches mechanical and electrical and material science and physics, and requires that not only deep knowledge but also broad knowledge at the same time. I think if you want to have a continuing cadre, if you will, of graduates who can think broadly and deeply about research problems and who will become future professors, you need them to come from a discipline that engenders that, and I believe that's nuclear.
You raise a good point, because so I mentioned earlier that I'm a mechanical engineer by training, but an aerospace engineer by practice. That was an easy transition because the general areas covered in both of those disciplines are the same. You have structures, you have fluid dynamics, all those sorts of things. It's been made clear to me many times that nuclear is different in that regard, that you really can't take a traditional engineering degree and add on nuclear to it and get to where you want to be. I mean, is that the essence of where you're going with this?
I think that, yeah, more or less, it's the ability for, I feel, a nuclear engineer to be able to communicate and understand the problems of the other disciplines, both at a 1 foot level and also at a 50,000 foot level, and in short, think differently.
Yeah. John, your thoughts on the topic?
As why nuclear, the obvious that a lot of people were talking about, of course, is the application of nuclear to our problem with planetary warming. And this is a really significant problem that we have to deal with. And, it's painful to watch what has gone on with regard to large nuclear power plants, and our difficulty in siting those or constructing those facilities. And so, for example, this project Pele, very exciting to me, that if we can build facilities that are smaller, reactors that are smaller and transportable, much of the trouble that we've come into with regard to the larger nuclear facilities are something I don't know anything about, and that much is economics. And that the facilities have gotten to be so expensive that the cost of financing these facilities is, dramatic. And the fact that we're building these and we don't know exactly how much they're going to cost is another problem that impacts the financing of these facilities. And so we desperately need nuclear for the climate problems that we've got that are real and apparent. And that hopefully if we can get small modular devices like it will come out of hopefully Pele, that then we can position them and have a knowledge of how much it's going to cost, that it's not going to be a massive investment. It can be placed at a point in the grid where it's needed. We don't have to wait 10 years to construct it. It can go in right now. I can remember the chair of the NRC once at a meeting said, look, if a utility executive, here's a question for a utility executive, needs whatever, 60 megawatts, in this point of the grid, are they going to go and put a nuclear reactor in there, or are they going to pick up the phone and call GE and drop a gas turbine in there? And, as far as that is the...
If we can hold off on this, we're going to come back to nuclear power. I'm specifically talking about a nuclear engineering program. We gotta go. So let me flip the question around. For those of you that have had experience with nuclear engineers, what would you do if nuclear engineering as a discipline went away? What would be the alternative? Or is there an alternative?
I think Ameren would have to seriously consider shutting down the Callaway Nuclear Center if it didn't have a steady supply of reliable nuclear engineers.
What would be the alternative in the federal government? Either Ben or Robin.
I don't think there is one. When you said that, what if nuclear engineering went away? I kind of recoiled. I was like, wow, that would be, in my opinion, catastrophic, both academically and also, in terms of power generation. I can't. I mean, because I'm from a different generation, nuclear power has just always been there. I grew up 25 miles from the Zion nuclear power plants. And I remember many times people saying, that's one thing we can definitely count on, is that we're always going to have consistent, inexpensive electricity because of that plant. It wasn't the only plant in the area, but it did make a difference. So if the entire discipline went away, I do not think there's a way to replace it. Not even in the aggregate. I don't think you could replace it.
Robin, your thoughts?
So I don't know what alternative we would have. I think the closest we would get would be to funnel students to physics and really focus on the nuclear aspects of physics, but it wouldn't solve the problem, and I really don't think it would be a viable option in the long run.
Let's pivot back to where John was going, and that is nuclear as an energy source. So nuclear energy currently makes up about 20% of the U.S. national energy portfolio, and it's also now viewed as an alternative to carbon sources. It's a carbon-free source. We even have Bill Gates as an advocate, and there's a lot of momentum in the popular media. So I guess the question is, are we on the verge of a nuclear renaissance? And will we be seeing an increasing emphasis on nuclear energy in the near future? Why or why not? I'll just tell you a little anecdote. At one point in my life, I lived in southeastern Virginia, and there was a nuclear power plant going in nearby. And at that time, there was a lot of turmoil about a nuclear power plant. And yet the public ignored the fact that just 20 miles in another direction, the Norfolk Naval Station was filled with nuclear power plants. In fact, they were even storing nuclear waste on barges in that area, and it was unnoticed. And so, where do we stand with the public perception of nuclear power, and is that going to change also? So, your thoughts?
Well, I can start. Obviously, you're right. The nuclear is carbon-free, and it's a renewable. It's better than a renewable source of like solar or wind because it's not intermittent. So it's on all the time. You can count on it. It's there when you need it. Sometimes when you need power, the sun isn't shining or the wind isn't blowing. Nuclear produces carbon-free power continuously, but the plants are extremely expensive to build. And the construction cycle is years. The interest rates on borrowing money, if you don't have a very cooperative regulatory system, it's just impossible to build. In Missouri, we don't have a regulatory compact that would allow you to build a nuclear plant anymore. Just way too expensive. You can build a gas plant in a matter of less than a year, and gas is cheap. It's not as good as, it's not totally carbon free, but it's certainly a lot less than, like you said, coal or something like that. Nuclear is small modular nuclear is attractive. We do have small modular reactors in submarines and aircraft carriers, but those are all owned by the federal government, and they're sealed reactors. They tend to use highly enriched uranium, which they don't replenish, they don't refuel. And those aren't allowed to be owned by civilians according to current law. You have to have a reactor that uses less than 5% enriched uranium. So it's several problems to get over. One is you're going to allow civilians to control bomb grade uranium in great quantities. Are you going to develop small reactors that can be refueled regularly, which we haven't been able to do yet? And so there's a lot of problems with nuclear in the future. There's only 2 plants being built in the United States right now. They're both in Georgia. There hasn't been any built in previous at least 20 years, maybe 30 years. So we'll see. And those 2 plants are very expensive, and they're taking a very long time to build. So it's kind of making it not looking any better about building nuclear in the U.S.
Do you see a prospect for a change in the regulatory process?
You know, I would say I don't think so. It's mostly because people they're nervous about nuclear anyway. And then you're going to tell them that your local utility company is going to own a bomb grade material. I think that's good. That's a tough push.
Yeah. Other comments out there?
We have one.
Okay.
How do you overcome the political opposition to nuclear?
So I don't know if you heard that. The question is, how do we overcome the political opposition to nuclear?
Well, the selling points are, certainly that it's carbon free and it's non-intermittent. It's a very reliable source of power, been handled very well. If you look at the Institute of Nuclear Power Operations, their data on the US power plants, they operate, I'd say, a factor of 10 to 100 times better than the rest of the plants around the world. So they've proven that you can operate them well, you can operate them safely. You do need a fairly intrusive organization like INPO in order to make sure that they can be operated safely. But it's a tough way to go.
There was a comment that just came up that 20% enrichment is not bomb grade. So there's still there may be a middle ground that gets us to where we need to be.
Yeah, I wasn't speaking about the possibility of new ones that are small like that. The ones that we have now, the existing small nuclear reactors are all have highly enriched uranium in them.
Is there a role that a university has in helping shape public perception? The challenge is that there's reality and then there's misinformation. Who's the arbiter of that?
I'll just say I think that universities, as the as the fount of knowledge, have the opportunity to do outreach with public schools, for instance, and educate young people early on as to what nuclear really is, so that their understanding is based in fact rather than fiction, and let the young people decide for themselves rather than simply be informed by what they see in the movies.
And what does everyone see as the prospect for the small modular reactors? Is that reality? I worked with a nuclear engineer about 15 years ago, and he was talking about the neighborhood size sealed systems as being the future. That didn't quite pan out. I mean, since the DoD's had experience with that, do you see that as a viable prospect for nuclear energy today?
Well, when I was at Ameren, I've been retired now 7 years, so I can't tell you what's actually going on right now. But we had an opportunity to work with Westinghouse on developing a small modular reactor. I think it was around 300 megawatts, and they had pretty advanced design on it. And in fact, the traction was that they were planning on manufacturing them in Missouri, mainly because of the association between Rolla and Columbia, that both could contribute, expert engineers to help with the process. But the federal government went with other people that were already developing small modular reactors. But again, these were sealed units that had never been built for refueling. Yep. And it turns out that they never were able to develop it to the extent that you could actually commercially sell them.
What did you see as the biggest hurdle to development?
It's just that they didn't have the experience of how to handle refueling cycles, and that was the trick. The trick was, how are you going to refuel these small modular reactors?
You know, one thing I will interject here is that the one thing that I see happening is that DOE is investing heavily now in research to support small modular. And the extent of the investment is significant. In and of itself, this is good news for academic units, but at least this desire to develop these small modulars has survived across political administrations now, it appears. And so there is a lot of momentum in this area. So I think as far as the university academic units, the best thing that they could do is do high quality research in support of this small reactors, microreactors, small reactors, and make it viable for utilities to be able to buy nuclear reactors that aren't so expensive, that don't have to be financed, that are predictable in their performance and the cost of the system. That would be the way to promote nuclear. I personally think that obviously there's people who will always be anti-nuclear, but I think most people would accept safe, small nuclear reactors, particularly in the context of the challenges we face with climate.
And well, thank you. I have one more question for the whole group, and I'd like your comments on this. And that is, as we embark on our journey to elevate the new department at S&T, what advice would you offer us?
Well, after all the comments I made about small reactors, I think figuring out developing some research into how to, refuel a small reactor would be a giant step in the right direction.
This, Robin, I think one of the things that you need to do definitely is show the wide variety of options for nuclear engineering. I mean, we've walked through the climate and the reactors and things like that, but there's also the defense aspect, not just the weapons side, but there's other places that nuclear plays a pretty significant role in the submarine fleet and things like that. So what are the options, and providing, here's the grocery choices that you can pick, as opposed to, if you do this, you're going to go into reactors.
A couple of questions. One is, how do you handle waste from the microreactors?
The question is, how do you handle waste from microreactors? I guess one obvious question: if it's a sealed unit and not refuelable, then you just bury it and leave it there. Yeah. Tom, you were going to say something?
Well, the federal government was supposed to be responsible for all nuclear waste at a permanent federal depository. Of course, they haven't developed that yet. So now, is around the country, there's been regional depositories been developed, some cooperative and some just standalone. Callaway has its own place to bury or to store nuclear waste. The problem is, really, with nuclear waste, nobody really wants to put it in an irretrievable place because it's got so much energy left in it that you'd want to be able, as science develops, you'd want to be, hopefully someday, be able to pull those out and pull the energy out of them. So it's tricky about how you dispose of nuclear waste, and that's what's caused the whole problem with the whole government.
I think you're giving us an excellent lead into the second panel. There's going to be some discussion about that topic there.
John Warmack has great ideas on those as well. So maybe John wants to say a couple words about that.
John, do you want to comment?
Yes. Can you hear me?
Yes.
Okay. Back to your prior question, what should the university science and technology take into account? And that is, one of the huge problems today is credibility. The public opinion polls about where Congress sits today is less than 13% credibility. The administrations in the past have got poor credibility, and the public needs to be able to look to leadership to be able to say, this is the golden standard. These people I can believe. So what science and technology, your institution must do is put forth maximum effort to maintain that credibility. And I can give you examples of where it didn't happen. University of California, Berkeley released some reports concerning we can power the United States on 100% wind and solar renewables. And when that went through peer review, it came back with a scathing. It was remarkable to me to watch the debate wound up in litigation, and the professors at Berkeley wound up paying the legal bill for the peer review group that did the challenge. So credibility is absolutely a must. The second thing that's important that we haven't discussed is the politics. And with regard to that, it's complex. We'll do that in the next session. But you have to have the economics. And when you start going small modular, the existing nuclear fleet is struggling with a single reactor. 2 reactors are much more economical. So the data indicates bigger is better for economies of scale, not going smaller. And I'll address that a little later, but I'm concerned that because we have self-imposed political constraints, we're letting politics drive engineering, and that is fundamentally why we're stuck in the United States today. And we have to break through that political barrier, and it can be done, and I'll address that a little later. But to your point, credibility for the university system.
Okay, great.
Oh, Rich, one of the other questions that came through is related to that, and that's how can you educate the general populace?
I don't know if you heard that. How can you educate the general populace? What's the mechanism that you reach out?
Well, one of the proposals that I've made to the Department of Energy was specifically funding for the decision makers. So let's suppose that I am a state rep in the Missouri legislature or in the state Senate, and we are proposing to do a facility in my county next to my city. That means that Missouri Science and Technology would roll out an education program so the decision makers will be able to make an informed decision, because today the default position for everything nuclear is negative. It's not even zero, it is negative. And that position has occurred because of politics, and the way we overcome that with education. You're in the education business. If you have credibility, you can explain it. There are some ways to make that available to the citizens, and they will become comfortable with it. Now, a couple of things I need to follow up and give you the proof of how that works. Around the world, nuclear has continued to fail, except for one exception. And that is when Finland went to build their geological repository, the citizens that were not opposed to it were connected to and approved it because they were proximate to an existing nuclear facility. Same thing for Sweden. Now, I've got an interesting story when I was promoting nuclear, and that was I was dealing with a county judge in Texas, and he immediately said, I am not interested. And through politics, we basically threatened him pretty good. That's a different story. And he came back and said, okay, I'll agree to support this, but I really don't like it. In summary, he's a business guy. He owned a Kubota dealership close to Arkansas Nuclear One. Never thought anything about it. When he talked to his equipment manager, he said, what do you know about the nuclear power plant? And he said, we would not be in business but for the employment associated with it. Well, it's not safe, was his position. And he said, my cousin is the director of safety. It is safer than any coal-fired power plant. Look at our record. So what happened is the point of my story, those people who are close proximity and know it will support it. But if you get outside that very close range, it doesn't happen. The last one was, as we made a presentation at the Argonne National Laboratory, and a couple of people that went with me spent time on nuclear submarines. And because they lived on a submarine in close proximity to an awful lot of stuff that was nuclear, they said, why are people afraid of it? And the answer is it's a lack of knowledge, which is education, which is the business that you're in. And with a concerted effort of a lot of people pulling in the same direction, this is a very doable project because we have no choice. As Dr. Degani said, there is no other solution than nuclear. Last comment I'm going to make on that one is when people say no nuclear under any circumstance, I said wind and solar is nuclear. It's just a big reactor in the sky, and that's what's powering Earth today. And we need to harness it a little closer to home than being out in space. Thank you.
I like your last comment. It's right on target. Let me ask John this, because he's working the nuclear medicine side. You know, you've got a cyclotron in the hospital. No one seems to worry about that. And so why is nuclear so well accepted in medicine when it's feared in other applications?
Yeah, I mean, that's a good question. I mean, people don't. I mean, it's clear that, you know, if somebody has a child and they have to have a CAT scan from top of their head, you know, the top of their head to their toes, they think it through. But it's it has to be described in terms of cost benefit. And, you know, particularly for somebody my age, am I concerned about taking some dose? Is it possible that it could induce a cancer 20 years from now? Well, you know, if I'm around 20 years from now, that'll be a nice problem for me to have, you know, to worry about. So I think, yeah, I don't see the issue. People, there are some people who are concerned about procedures that they receive some dose for, but generally speaking, people take nuclear medicine therapy or treatment, and it's not a problem.
Now, coming back to my prior example, in the national security arena, there doesn't seem to be the same sort of fear there is for commercial plants. Any ideas on why that's the case?
I think there's a fear of the use of nuclear energy and the nuclear portion of it, but I agree. Everyone expects that we are going to have a deterrent that is a nuclear deterrent at some level, and you've got the pluses and minuses of the folks who like and don't like that, but there's not great other options. And as we've been living with them since the 40s and 50s when we went into larger scale production, I think it's pretty accepted.
Rich,
Yeah, go ahead.
there was a question in the chat related to low pressure molten salt, and I believe Jim Kennedy had expressed that he wanted to respond to that. So Jim, maybe you could paraphrase that question and respond.
Oh, am I on now, or what do I have to do? Here we
You're
go.
on. Okay. Go ahead and talk.
Okay, so yeah, I'm just making the point, a lot of the issues here are how do you overcome fear of nuclear, misunderstandings, and you can list all of it essentially as 5 points. People think nuclear reactors blow up. Of course, we all know that's not what happens. They know that they melt down because they saw a movie about it. Of course, we all know there's widespread radiation, which causes all these sea monsters to come out. And then there's weapons conversion issues. And then the one we've just been talking about, which is waste. And one of the problems with the nuclear industry is that it knows what it knows and it wants to do what it knows. So we basically are stuck in the light water paradigm. And as long as we're stuck in the light water paradigm, those 5 things can't go away. Alvin Weinberg knew that. And when he went to Chet Holyfield, who was the chairman of the Nuclear Atomic Energy Commission, he explained this issue, the inherent safety issues in LWR. And Chet Holyfield famously said, if you continue to put safety first in nuclear, you need to find a new job. And that's kind of been the message. So, you know, John and I, of course, maybe we only have one horse to sell, but the horse we want to sell solves every one of those problems, and it's proven. So, you know, we'll get to talk some more about that. I didn't mean to jump in. I was just.
That's okay.
So anyway, it's very important. And one of the questions you had asked was, what are some other things that MS&T should focus on? I think maybe you should broaden the discipline of nuclear to include things. I know that John Kutch and the Thorium Energy Alliance have produced an academic product for universities to teach molten salt. And there's other things, of course. There's lots of other technologies, and I think all of them should be looked at and understood. But spending a long time looking at this issue from my perspective, you know, I guess all nuclear advocates just become cults, right? Because you just like what you like. But anyway, that's where I'm at. Sorry, I didn't mean to jump in.
That's quite all right. In fact, if any of the other panelists from the second panel want to weigh in, please jump in at any time.
This is John Warmack. With regard to follow up on that comment, is nuclear is bigger than nuclear. The legal aspects of nuclear are huge and complex. You ought to look at all of the court cases associated with what are the rules and regulations. So the university, by its very name, has the College of Engineering. It has the College of Nuclear Engineering. It has a law college on the Columbia campus, probably St. Louis too. So to answer your question, to make this successful, we need to pull in all of those disciplines, including political science, so that how we message what we're trying to get accomplished is critically important. Because if we don't get this right, there is no solution to the big picture climate change issues. And eventually, fossil fuels are finite and we will run out. With regard to nuclear, even though that is finite because of its energy density, E equals mc squared for mass defect, the number will power the United States for hundreds of thousands of years into the future, and no other power source can make that claim.
You raise an excellent point, though, and that is we talk about multidisciplinary problems, and often we talk about that in terms of multiple engineering disciplines. But what you're really saying is to solve the nuclear problem, we have to bring in a much broader array of disciplines into the focus. I think that's an excellent point.
I'd like to build on both Jim and John's comments. I think, and I don't know if you have this already, a class on just Generation 4 reactors. You could spend, you know, an entire class on any one of them, but just learning about, you know, these are the kind of reactors that you can expect in the future, and then with an entree into Generation 5 reactors and working with the very much cutting edge designs. In addition to that, with what John said and broadening, I think one of the ways that you could go about doing that is the way that computer science has sort of done it in past, say, 10 to 15 years. They have here at University of Illinois called CS Plus, which basically means computer science plus some other specialty, and they have double degree programs. I'd like to see nuclear plus, where it's nuclear plus physics, nuclear plus material science, nuclear plus, you know, just nuclear plus political science for that matter, where you train people to have the solid foundation of understanding of how it works, but also allow them to broaden in another area. So when they go off into another field, which may or may not be nuclear proper, kind of like I did, they can bring that understanding along with them without sounding strictly like a scientist, as Jim said, who likes what they like. They actually say, well, I've seen the other side. I understand the other side. And here's my rationale for this.
That's really an interesting point. I'm thinking of plus topics, and I've heard law, economics, politics. Any other thoughts out there on what other nuclear plus areas make sense?
Okay, John Warmack again. Can you hear me all right?
Yes.
Okay. One of the most interesting things to me from a big picture public policy is the Biden administration's reach out to Iran to restart a agreement to do not nuclear proliferation. And when you look at the benefits of an advanced reactor fuel cycle, the negotiations for national security completely change. We're going down path A based on today's technology. But should we roll out a different fuel cycle, those negotiations with Iran and national security for the world completely change. The paradigm shift, what occurs as a result of it. And our current political leadership does not have a clue on the details of how the nuclear fuel cycle works. Most interestingly, we are in the shape we're in because of a debate on the Senate floor that took place in 1994. Go read what Senator John Kerry had to say at the time. He completely missed it. And currently he is a senior leader in the Biden administration. The president participated in that floor debate, and ultimately that was an issue to kill EBR-2, and they managed to accomplish it. I don't think they intended to do it, because what we know now is that was a mistake. And the beginning spot politically is to go back to that floor debate on the Senate, figure out what went wrong, have a person at Missouri Science and Technology and other institutions of higher learning set the record straight with regard to science and technology, and then let the politicians readdress that issue. But it's a fascinating thing concerning how far the politicians were off during that floor debate.
And that's an education perspective, right? I mean, they really need to understand the problem. I also heard a recent quote that the United States was going to take a perspective of eliminating CO2 from the atmosphere. That's the level of understanding we sometimes have of these things.
Exactly. And the thing that was interesting, we were having the discussion of the uranium fuel cycle versus plutonium. When you look at the fast reactor technology and say our starting spot is, let's say, 100 gigawatt days per metric ton, then the isotopic distribution in plutonium changes significantly, which makes the building of a nuclear weapon virtually impossible because of how physics work. And that was completely lost on the politicians, and that's an education issue that needs to be addressed. For example, you have 2 U.S. senators. Hopefully one of their staff is listening, and they need to be paying attention to this, because this is a political problem. It is not a technical problem.
Great, thank you. We have time for one more question, and we have a question that came in.
Right, and this, Rich, may also be one for you as well as panelists, because it has to do with education, and it has to do with the nuclear plus comments you're making. How would you advise recent mechanical or electrical engineering graduates to get involved in nuclear engineering?
Well, I think the one direction is to pick up a master's degree or a master's certificate. I think the burden will be on us to design these so that they can be taken by people that don't have a nuclear background. Other thoughts out there on how how we can get nuclear engineering into the hands of someone who has a bachelor's degree in some other area of engineering.
I can just quick say, working at federal government labs gives you an opportunity to do a lot of cross-cutting work, and they'll just naturally have the opportunity to work with other people in other fields. Some of them hopefully will be nuclear, especially at the DOE labs. And then that may actually spur them to say, hey, I want to go get a master's degree and change specialties.
Any last thoughts on that?
I think working, as you pointed out, the national labs, just in the industry and everything that supports that is really probably a great entree into nuclear engineering.
Okay, with that comment, I want to thank our panelists and everyone else who entered into the conversation. I think it was a very dynamic and enlightening conversation for me, at least. And excuse me, I'm sneezing. We're going to take a 5-minute break, and then we'll do the second panel. So again, thank you all, and see you in 5 minutes.
Hello, everyone. Good morning. My name is Angela Lukien. I'm the Associate Dean for Research in the College of Engineering and Computing. Any good department has good education and good research. Research keeps our faculty active and engaged, and it helps them think like students. So our second panel is on opportunities and risks. And really the focus there is on new technology, new developments. What are those opportunities and risks? We have 4 panelists joining us for panel 2. John Wagner, unfortunately, had to send his regrets. He has sent his Associate Director of Idaho National Lab, Jess Genn. Welcome, Jess. Thank you for joining us. John Warmack, who you heard a little from in the first session, is the founder of Warmack and Company. Jim Kennedy, president of 3 Consulting, and John Kutch, the executive director of Thorium Energy Alliance. So as before, we're going to give the panelists a few minutes to introduce themselves, introduce the audience to their background, and then we'll pick up with the questions. So Jess, would you like to go first?
Yeah, absolutely. Good morning. Can you hear me okay?
Yes.
Okay, great. So as you mentioned, I'm Jess Jean. I'm the Associate Laboratory Director for Nuclear Science and Technology at Idaho National Lab. I'm standing in for John, who regrets not being able to make this meeting. I am qualified for this panel, given that my first name starts with J, like all the other panelists. So happy to be on the panel. In my role at INL, I'm responsible for much of the nuclear-related research and development, particularly DOE R&D programs that include reactor technology and reactor demonstrations that are going on. INL is DOE's lead nuclear energy lab, and we have a number of things moving forward. I think everybody's aware of the history of INL, where we operated 52 test reactors over our history, but most of those were in the distant past. We're now looking forward to several opportunities to demonstrate new reactor technologies we call advanced reactor technologies related to a reactor that we're developing called Marvel that will be operating in the 2023 timeframe, working with the Department of Defense on their Pele microreactor project, working with the private sector through the advanced reactor demonstration programs, which includes a molten salt reactor demonstration on our site, as well as a versatile test reactor and a new scale small modular reactor on our site towards the end of this decade. So this is very exciting, very new to be in the business of developing and demonstrating and building reactors again. So that itself creates a lot of opportunity. The other opportunity I want to mention is related to how we intend to use reactors going forward, which could be quite different than the single purpose of generating electricity. Many of these reactors produce high temperature heat that can be used for hydrogen production and other industrial processes, and we're doing quite a bit of research in that area as well. So with that, I'll stop and we can move on to the next panelist. Thanks.
Thank you. Our next J is John Warmack. John, can you tell us a little bit about yourself?
Yes, I'm a graduate from, at that time, University of Missouri-Rolla, and it was a wonderful education. It gave me the ability to see the world from a different perspective, and from there, I went with our family business and spent most of my time dealing with government and government relations. So with engineering and government relations combined together, I view this problem a little bit differently than maybe just from an engineering perspective.
Okay, thank you. Our next panelist is Jim Kennedy. Jim, could you please introduce yourself?
Hi, Jim Kennedy. I'm a regional folk here. I own an iron ore mine about, I don't know, 45, 50 miles from MS&T. It has a world-class rare earth deposit. And I had spent a lot of time trying to figure out how to monetize that rare earth deposit and realized that our country was 100% dependent on China, and went to Washington, D.C. about 12 years ago to explain that to folks at the Pentagon, and bumped into a guy named John Kutch, who was really interested in some of the issues related to the rare earths and our problematic byproducts like thorium and uranium. So John and I have had a dog and pony show going on in Washington, D.C. for over 12 years. John and I have authored a bill that's become a bill in the House, in the United States House and Senate. It was offered up 3 times as an amendment to the NDAA, which is the National Defense Bill. It was offered up again in the House and Senate in the previous Congress, and we believe the bill will be offered up once again in the current Congress. The bill solves some problems related to rare earth production, how to deal with those pesky actinides, and the bill also creates a government-sanctioned platform for the development of thorium energy systems and other things. So I don't know, I think that's probably my time limit. So I'll drop out now.
All right, thank you. John, you got a mini introduction there, but why don't you fill in the blanks? Can you tell us a little bit about yourself?
Yeah, do you want to wait till our panel for me to show the little slides I
No,
put
please show them now. So
okay, I'll just share my,
I believe you should be able to share your screen.
yeah. All right, so does everybody see my pretty little screen there?
We do.
All right, good. So I'm John Kutch. I started the Thorium Energy Alliance with a few other folks informally about 15 years ago, and then we became an official 501c3 educational advocacy organization. And since then, we've been trying to promote the use of thorium in everything from molten salt reactors to advanced materials. So the thing we do is not just energy, right? I should have jumped in on the other talk, like what should people know about nuclear that isn't just energy and electricity. And we need radiochemists. We're desperate for radiochemists. We also need mining engineers who know how to mine actinides and elements that present a radioactive signature. So that's part of what we're doing right now. We're actually working at the University of Missouri, St. Louis, UMSL, to do some of this work. And but obviously we have a great interest in reviving the idea of using thorium as a relatively safe nuclear fuel. And as Jim and I will talk about, you get the most attractive thing to me about thorium, besides being pretty easy to handle. You use it in its natural state. You don't need to enrich it. You also get it for free when you process rare earths, right? So right now it's a waste product or a byproduct, and we'd like to make it into a valuable material. I can pop these slides back up later, but this is a representation that my engineering company developed, and Idaho National Lab developed that flow graphic in the upper right-hand corner there. And all these are available at our website, thoriumenergyalliance.com. Videos, articles, illustrations, if you ever want to learn more about thorium and its uses. And I won't be, I'm not a monster. I won't read the slide to you. So I figured you all know how to read, but there are some really, if you look at those bullet points up there, you can see why it's so attractive to develop these molten salt reactors, especially molten salt reactors, in my opinion, that use the thorium fuel cycle. You get a lot better utilization of the fuel. They're inherently safe. They perform in a very high temperature range that allows you to make process heat, right? So the stupidest thing we could do today is make electricity, right? Electricity markets have been ruined by renewables and subsidies and tax credits. But what we could do is co-locate these relatively small but very powerful reactors with oil refineries, steel mills, concrete facilities. We could even be smart and cascade the heat. So if we start out with 600-700 degree heat, we could make hydrogen, and then we could do some work in the steel area, and then we could cascade down to desalinating water, and then come back around, maybe do some district heating, and then go back into the reactor. I mean, that's a very simplified idea of multiple bites at the apple, but it gives you an idea of way more than just electricity that we can do with this. And what Jim was talking about, the bill, what used to be called S-2093, we're waiting for it to be reintroduced. And we have great confidence that it and the House version will be reintroduced. But right now, one of the things that we're working for with Oak Ridge National Lab and through a program called GAIN voucher, if you're not familiar with it, one thing that we're working very hard to do is develop this thorium bank concept, because Jim Kennedy has a mine that is going to generate a side stream of rare earths. And now, while Jim has a very, very low amount of thorium, it would be an excellent demonstration that we could take the actinide side stream off of that rare earth side stream and store it safely, encapsulate it, you know, keep it inside a facility, and maybe some future generation who's smarter than us will find uses for it. But all that matters is that those set of words up there that are surrounded by the glowing green box, if all we did, if all Thorium Energy Alliance got to do was store the thorium and eliminate that liability, it would instantaneously reactivate the critical materials industry in the United States. And that would be hugely beneficial to everything from solar, wind, jet engines. Nuclear power needs rare earths, and right now there's a single source supplier for rare earths on planet Earth. So we have a huge interest in just doing even that little basic part. And then I'll just leave you with this final slide. If we don't do it, I'll tell you who is doing it. You know, China is committed to doing it. They're spending billions of dollars doing it. They aren't screwing around. That is a real reactor there you see in the lower left-hand corner. That is the thorium molten salt reactor. I think it's called the FL1, used to be called the TMSR2, but that's a real building, all right? There's no molten salt reactor building anywhere else on planet Earth, all right, except for an abandoned one at Oak Ridge. You know, so China understands this. That slide in the lower right-hand corner is from Synap. You know, they understand if you make a molten salt reactor, look at all the other things you can do. You can use concentrated solar. You can use wind to feed into a common molten salt pool of energy, and that molten salt will allow you to do hydrogen, chemistry, steel, cement. China is doing this, and they are going to shred us alive because they will have the cheapest, cleanest energy on Earth, and they will export it all around the world. And so, but we got to, you know, they might be pitching at windmills, but I am committed to the fight that we can do this too. You know, we used to do it all the time. As Jess said, INL used to have 50 plus reactors. We used to build a reactor a year. You know, I believe we can get back to that. Thanks for your patience. That's my introduction.
All right, thank you very much. So I could tell from the first panel, this is going to be a very heated and interesting discussion. But first, we want to pick your brain a little bit on our new nuclear engineering and radiological science department. So the first questions are about that. Question 1, continuing on the themes of where we need to go with this new department. As we grow and hire faculty, the chancellor mentioned that our very first Cummer chair will be the chair of nuclear engineering and radiological science. What would a dream team look like in terms of faculty expertise? What skill sets are on this dream team?
All right, maybe I'll get started here. And you know, there are aspects of this covered on the last panel as well, so I'm sure that discussion is going to carry over. Obviously, it's important, I want to start with, it's important to make sure you're covering the engineering fundamentals related to nuclear energy. And S&T does a good job on this, as well as other universities, but you don't want to lose that because that forms the basis of all communications and being science-based and be able to communicate that. This includes not only mechanical, electrical, chemical, I think John mentioned radiochemists, very important, but specific nuclear disciplines related to reactor physics, reactor system, reactor safety, reactor design. If we don't have the engineers able to support, you know, what's maybe more traditional, we're not going to be able to do the designs, you know, safety analysis and start the reactors up. So I think everybody's well aware of that. I also endorse many of the comments about the multidisciplinary and areas related to policy, communications, you know, broad education, social media and social aspects are becoming more important. And you know, in the history of nuclear energy, we generally have not paid a lot of attention to those, but they've become more important than ever to make the case for nuclear energy. There are emerging areas that, you know, I'd like to point out. This is across all engineering, but we want to make sure that nuclear systems don't fall behind. This is related to advanced materials, advanced manufacturing to reduce costs and create designs that would not otherwise be possible. Modeling, simulation, machine learning, those are all fields relevant to engineering, and turning those from, in some cases buzzwords to real practical use is something the department can focus on. That's all for me right now.
Jim or John, please go ahead.
I would say that from what I've seen, that the knowledge base has been mostly lost. I mean, everything from just simple stuff like knowing how to use remote manipulators, glove box techniques. You know, I have to be a little bit careful about you know, stepping on people's toes, but I've seen a lack of skill sets, right, from laboratory techniques, things like not even knowing how to do a crystal melt test, you know, and it just shows you that the infrastructure supply chain in education and the laboratory environment, you know, that very base of the pyramid isn't even there anymore. And then you go way up to something applied, and you look at Plant Vogel 3 and 4, and you realize, man, you know, all the cost overruns for Plant Vogel 3 and 4 can be traced back to nobody's built a nuclear reactor in 30, 40 years, right? And so that skill set that we had developed, you know, building 140 light water reactors from the late 60s to the mid 80s, you know, we built a huge quantity and we had a huge skill set, you know, Chicago Bridge and Iron, Westinghouse, all these companies that built it. And then that just evaporated. If you don't keep building them, you know, that knowledge base goes. So, you know, it starts with the schools. We've got to get back to like core hands-on. What I don't like are these schools that just have virtual learning, right? You know, learning about nuclear engineering, like U of I doesn't even have a nuclear reactor anymore. How do you learn about nuclear engineering if you don't have even a little TRIGA or something? You know,
The answer is actually they contract with us and do it. Virtually.
Yeah, well, it's not there, you know. So, you know, but see now, Christian Abilene University, you guys should look up. They're trying to build a molten salt reactor, a little one like the Chinese, like a 1-2 megawatt reactor. And I give them all the credit in the world, you know, that they are going to try and build the first new university reactor in decades, and it's going to be an advanced Gen 4 molten salt reactor. So look that up.
John Warmack.
With regard to the question of how S&T manages the program, I would suggest that the most important aspect is supply and demand. And if you supply a lot of talented people, but there's no demand for that talent, that mismatch will create difficulty. It's an inefficiency. So with regard to how that gets done, we need to be able to have a smart national energy policy that is outlined, that shows where we need degrees of expertise.
John, you're cutting out. We've lost you, I think. There you are. You're back. You're on mute. You're on mute. There you go. There you are.
Okay. My internet dropped out. So the supply and demand, and this is a unified effort on the part of multiple disciplines, because just to have a big pool of talented people with nowhere to go, that does not have a happy ending. And what I mean by that is when the Soviet Union collapsed into just Russia, the technology that existed in their nuclear industry wound up needing a place to go, and some countries that are adverse to the values of Western democracies picked up that talent, and that's how other countries advanced their nuclear weapons program, by having those people looking for a place to go. So we need to be very careful how that gets advanced. Supply and demand needs to be balanced.
Thank you. Jim, do you want to weigh in on this? You'll need to turn your mute off. You're on mute.
Well, I don't know what I can add. I think John's Warmack's last comment is, I mean, God, we get all excited about where we want to go, and then nobody can find the keys to the car, and John's the guy that says, hey, where are the keys to the car? A nuclear program needs a nuclear future, and that means that there has to be the political or industrial will to create an opportunity where your students go out into the world and they're in high demand. And man, that is the single most important problem to solve. And I don't know if that can be solved on campus, but I will throw a little whatever to some friends of ours. There's a guy named Eric Meyer, and he runs a little program called, what is it called, John? Atomic Generation.
Generation Atomic.
Generation Atomic. Yeah, I think we need, John Warmack is so right. I'm literally floored by what he said, because I'm all excited to go to Florida, but nobody's got gas money or keys. But yeah, that's it. I mean, that's the single most important thing. And to some extent, how much of that can happen on a campus? Well, that's kids realizing their future, the future of their economy, the future of the environment they live in, and what it's going to be like. And, unfortunately, by the time they get to college, they've already been indoctrinated with silly thoughts of unicorns and rainbow dust. But yeah, I can't add anything. I mean, the Johns and Jess, they said it all.
Thank you. Ben, are you still on the line? Ben Masters, are you on?
I'm here.
I want to I'm putting you on the spot, I know, but I first met you when you came to campus, and you were interested in workforce development, and you said, we have some keys to our car. Can you help us drive it? So could you chime in on this issue, please?
So long story short, the Army used to have a nuclear power school, which is what eventually turned into what is now the prime power school. And obviously they kept the power generation, but the nuclear part is gone. If nuclear power in the military, specifically the Army, is going to be a reality, even if you have walk-away safe reactors, you still want to have people there, who are aware of what's going on and understand it, and who are at least monitoring. And that takes some education and training that really doesn't exist anymore. The Navy has, obviously a complete school, but since they're reliant upon it for a different purpose, primarily propulsion, and it's obviously a different kind of reactor, it's different. But I do think that, there's been a departure. The fact that Missouri S&T is not exactly co-located, but I guess in Missouri, 25, 30 miles is no big deal. You guys being close, I don't see any reason why, your subject matter expertise couldn't be brought to bear to the prime power school or not the engineering school, primarily the prime power school. Actually, the Siberni school is there too. Yeah, so in both, I mean, it's a natural connection based just on geography and the pre-existing relationship that you have.
Well, I have to warn you, Ben, that the Dean and Chancellor just heard you say that, so I'll give them your email later. Let's move on to question 2. If we were to hire this dream team with the right skill sets, and what I heard from John Jean was that these are the basic undergraduate concepts, faculty equipped to teach those, how do we better engage this faculty with experts in national labs and practitioners in industry? In other words, with you. How do we work together in developing and deploying these new nuclear technologies?
All right, I can start and talk on behalf of the National Laboratory. I mentioned at the outstart a number of programs that we have, and a little bit related to the last connection. I agree with John Warmack as well, but I do want to point out that we do have several reactor demonstration projects that started both, and there's a need for expertise at the laboratories and within the companies developing this. So there are opportunities at National Labs through our R&D programs and coordination on these demonstrations. We regularly engage with faculty and students at universities through collaborative research projects, which could involve some of these projects I just mentioned. Collaborations on proposals, there are opportunities through the DOE Office of Nuclear Energy, ARPA-E, other organizations where we're very interested in collaborating and making our expertise facilities available and working with faculty and students. We obviously have internships and fellowships. We had, going back to 2019, last year was a bit impacted. We brought over 400 interns on the site during the summer, and definitely very interested in that. So plenty of opportunities. I think making the right connections between faculty and our staff is the key and probably the most difficult part. So that's an area to think about how best to do that, whether it's through visits, seminars, or other activities. Thanks.
John Kutch, how do we get our faculty involved with the Thorium Energy Alliance?
Just look us up, man. We'll take anybody. We actually got, it's a little side thing, but we actually got a lot of heat for that when I and the other guys started it. They're like, well, you're not serious. You just take any old person off the street, and these ivory tower guys, the head of Oak Ridge National Lab in the Washington Post said I was the captain of a boatload of fanatics. And he later apologized for it, but it's like, why don't we have more fanatics or at least enthusiasts? We were talking earlier about having the public buy into this. I have 5,000 people. Some of them are scientists and researchers, but some of them are just, folks that understand enough to realize that this is a huge opportunity. And oh, God forbid we have somebody who may have been a teacher or, a surveyor and not a nuclear engineer. They can advocate for it as good as anybody, probably better. I mean, the people whose job it should be to advocate for nuclear are cowardly, and the trouble is there's no such thing as a there's no such thing as a nuclear power company in the United States, right? They all have other dogs in the fight. So if Exelon says nuclear is the best energy, their solar division and their coal division get all weepy and cry because, but I always tell people solar and wind and gas need nuclear. Nuclear doesn't need them. And all these plans, of trying to integrate solar and wind and intermittent, very inefficient energy into grid systems that could be supported with nuclear, it's just crazy to me. Anywho, I hope that kind of half-ass answered your question.
Jim, do you have anything to add to that?
Okay, John Warmack, I'll chime in.
Okay.
From a very high level point of view, one of the concerns I think that needs to be addressed is the culture of the United States today. And what I mean by that is children today are exposed to what is perceived to be stuff that's cool. And that is the entertainment business as it relates to football or basketball, soccer, other things of that nature. And for a person who is not inclined to go that direction, where is the example of, man, it is cool to be a scientist? It is beneficial, and look at a career, a whole life, making the world a better place to live, providing basic services like power, like chemistry, like a safe environment. And that can be accomplished. That can be accomplished by having Missouri S&T reach to K through 12 through a coordinated program with the Department of Education.
I saw a couple thumbs up. Anyone want to add anything to this question? If not, John, the next question is kind of a softball to you. So I'm going to give you a warning. I'll call on you first. But let's focus for a moment on the downside of nuclear energy, and that's radioactive waste. What technologies exist to deal with this waste? Is there a technology or is this a technology or policy hurdle? And is there a magic bullet out there to deal with nuclear waste? So John Warmack, if you could please take that first.
Well, go back and look at any of the technologies with regard to a fast reactor, and it's not a problem. We will need a geological repository to take care of the long-lived radioactive elements, but there is technology where we could transmute it in a specially designed reactor. And if we just address the problem, we will get a solution to it. And currently, we're not even addressing the problem. Look at the EBR2. Look what happened at Oak Ridge with their molten salt reactor. I'll just add that the National Academy of Sciences did a very detailed report in about 2006 that ranked the probability of success for a fast reactor to deal with waste, and the metal liquid sodium reactor was what they deemed to be the best case for both economic safety and others. But the molten salt was right behind it. And why I am an advocate for the liquid sodium fast reactor is based upon the National Academy of Sciences report. I would encourage everyone to look at it, but at the end of the day, we just need to pursue an end product. And looking back to the NASA program, the Moonshot, it's very interesting. President Johnson was confronted with a war on poverty, a war in Vietnam, and the Apollo space program. And he didn't have enough money to do all of them. And Johnson overrode all of his advisors and said, I will not cut back on Apollo, because if We don't hold the date. If we don't do it, it will turn into a perpetual, never-ending research project, and we will have thousands of engineering studies, but we'll never accomplish the goal. And he said to his advisors, get us to the moon and then cut the program and we'll make the budget work. And nuclear engineering, nuclear deployment has done the same thing. We are in a perpetual research operation. We are not with a goal to make it happen.
That's
Jim,
right.
Oh, John Kutch, please go ahead.
That's I'm just giving them Jen the thumbs up there. The that is exactly what it is. It's endless tiny little research programs. This thing behind me, that represents billions of dollars and thousands of people and a real commitment. And we got into this crazy, horrible cul-de-sac of saying, oh, we can't pick winners and losers. And so we have a bunch of little teeny tiny startups, that raise a couple million here and there. And all they are able to generate are paper reactors and PowerPoint reactors. It's like, where is this thing in the United States or anywhere at this point? Brazil, France, I don't care. Somebody's got to make a counter to this, because that thing's gonna roll over us. I don't think if there's one thing we can take away, I know we're supposed to be talking about the education aspect, but I don't want students spending thousands of dollars and thousands of hours learning a skill that won't be applicable, because if the Chinese start sending these around the world, they're not going to hire locals to run them. They're going to bring their own staff, and they're going to have ring fences around them, and they're going to say, just plug into our grid. Don't worry about what's in that black box in there. We got our own staff. We got our own, dormitories. And so if we want our children to have a future, we've got to do something like John said. We can't do little teeny tiny niggling little experiments anymore. We're basically reinventing the wheel over and over and over again. If MS&T wants to have a commitment, that just goes back to, that's why I'm so pleased with the commitment that Christine Abilene and Texas A&M made, because they want their students to know about Gen 4 technology.
Justine, what are your thoughts?
A couple comments. First of all, the way the question was phrased about the downside of nuclear energy related to waste is actually, a positive. The amount of waste generated per kilowatt hour for nuclear, of course, is much lower than any other source because of the high energy density in the actinide fuels. And so part of this is a communication problem in communicating that the waste is a huge problem. I think both the Johns talked about the technical solutions available. It is stuck right now in making policy decisions. I did want to talk a little bit to John Kutch's point. I fully agree with, we need to move forward and build things, and have pictures like that behind John's head right there. DOE has made selections for the Advanced Reactor Demonstration Program with two companies, TerraPower and X Energy, to build demonstration reactors within 7 years or so. And these are multi-billion-dollar government investments with cost share as well. So, there are steps that are being taken. I think there is momentum behind building and demonstrating technologies again. So, just wanted to make that point. Thanks.
Jim, do you want to add anything? You're on mute. There you go.
So I know the original questions deal with how to build up a program. And, this maybe seem a little off track, but I'll get you there. So the problem today is, let's go back to my same 5 problems. They don't go away because we are stuck in a light water, solid fuel paradigm, and nobody can shift because the political system and the lobbying system in Washington, D.C. will not budge. They control this space. They can spin out papers. They can spin out articles and op-eds, and we can't move off of light water, solid fuel. Now, let's all be grown-ups. When they came up with the light water reactor, it was literally literally a first concept reactor. Put something hot in water, it will boil, we'll have expansion, we'll spin something. That reactor technology is just not appropriate because the cost of rolling it out is infinite. I mean, if you don't know what the project's going to cost when you're done, and if you don't know for a fact you're going to get a permit, then your financial liabilities are literally infinite. That's that little sign like this. They put it on a car. It sells cars, but it doesn't sell reactors. So get to my point. I will tell you this. John and I do a lot of outreach on molten salt reactors, and there are other excellent reactors, John, Warmack, that also fit the bill. But a molten salt reactor concept is so simple to understand, and the upsides are so enormous that I literally, at every school my girls went to, people wanted to have Thorium Energy Alliance stickers on their phones because they were cool. That meant they were thinkers, right? If you just educate people on MSR and other simple alternatives to light water solid fuel, they'll get so damn excited that one day they'll roll over this wall of atrophy and immobility, because it is what's killing the nuclear industry. The nuclear industry is dead by the sheer weight of light water reactor costs, risks, and unsurmountable issues. And it's time to move on. So maybe no matter what else, have a little intro program for, alternate nuclear energy. And man, once they bite that apple, they get so excited. It's unbelievable. I mean, like, I've created little armies of people that talk about this. I've interacted with people in their 80s, and they get so excited that they call me up. Like, John knows, John gets calls all the time. It's something people can get excited about, but no one in their right mind gets excited about light water solid fuel, because it's a first concept reactor that, despite its incredible safety record, is permanently tarnished with decades of PR campaigns designed to kill nuclear energy. So that's my best suggestion to you, is offer classes and alternatives, create a little army of people. There's this Generation Atomic. It's like 20-somethings running around, going, literally knocking door to door saying, you should be excited about nuclear, and here's why. But never going to happen with LWR solid fuel. It is the black hole of the nuclear industry. So that's all I can say. I will kick myself off.
Just told us in the previous question that communication, you all told us this, but he specifically used the words, this is a communication issue. So let me bring up another communication issue, and that's safety. The Fukushima earthquake in 2011 raised concerns about accident-tolerant nuclear energy, in particular, nuclear fuel cladding to deal with extreme events. What technological or design advances are needed to prevent the next Fukushima? Jess.
Okay, Don, do you want to go first? Good. So you come off mute.
Yeah,
Okay, I'll go ahead.
Yeah, go ahead, Jess.
Okay, let me just say a few things. I think there'll be some good discussion on this question. So you had mentioned the nuclear fuel cladding, and I think that question is being a bit specific, because reactor safety is a reactor system, needs to be a reactor systems approach. So if you look at Fukushima, while the cladding oxidation and fuel melting, was a result, the real issue was continuing to cool the fuel, and the current light water reactors ultimately require backup power to do that. Of course, Fukushima lost that, and the result, is apparent there. So to address that in the light water reactors, you have to do things to ensure you keep the reactor cooled. is one approach, and there are activities to do that. There's backup systems. U.S. industries introduced their flex system to provide, additional backup power when needed. Another approach is through technology, and again, for light water reactors, it's looking at alternative fuels, accident-tolerant fuels, advanced technology fuels to support that. And then the third way, and we've already talked about this, is looking at different reactor system technologies based on different coolants, different technologies, and of course that's being developed as well, and they're extremely important also. So I think it's broader than just looking at the fuel. It's looking at the whole system and improving the technologies that can avoid these types of events. Thanks.
John Kutch?
Yeah, if you're talking about the solid fuel, I mean, there's, that's another kind of sad thing. The accident tolerant fuel program was, I think it was pretty successful. After Fukushima, they expedited a lot of the work with the accident tolerant fuels, and then there's been accident tolerant, and you could argue better fuel form factors out there for decades. Lightbridge has a thing they call their cruciform fuel, and it's when you look into it, it's arguably a very interesting way to do the fuel, and it's just one of these chicken and egg things. They need to fabricate some fuel and test it in an actual reactor, and I begged them to try and test it in the Kewaunee nuclear reactor in Wisconsin, because one of their, I won't get too deep in the weeds, but if we're going to shut down these reactors, why don't we use them for research purposes? If we're going to keep the light water fleet running for another 20 or 40 years, let's take some of the ones that were thrown on the trash heap. Today, Indian Point is shutting down as we speak. That's a several thousand megawatts of clean power. Thanks, environmentalists, look what you've done. So it's like, why don't we make lemonade out of lemons and use the existing fleet? And then of course, when you go to Gen 4, the very heart of the definition for Gen 4 reactors is that they're inherently safe, right? They're walk-away safe. Through their physics, they can't explode or melt down, or many of them don't use water as a coolant. And that's why the molten salt reactor, that's why I've dedicated 15 or so years of my life, because I see the vast advantages. And I won't, we're not here to do a symposium on that, but you certainly have plenty of resources. You go to thoriumenergyalliance.com or watch the movie Thorium Far Side of Nuclear or Pandora's Promise. There's a lot of movies out there that talk about the state of advanced nuclear and talk about why they're advantageous. So I think this idea of safety, preventing another Fukushima, that goes back to this fear-mongering. No one died from Fukushima. People died from a tsunami, and after the tsunami, they died from an extreme overreaction. Now, the TEPCO is, horribly at fault for such a stupid backup power system. Don't get me wrong. That was a travesty and an insult to the world. But the release didn't kill anybody. People aren't falling over with tumors. The people who died because they were sent hundreds of miles away and evacuated from villages that should never have been evacuated. So it goes back to, how do we make the reactors safe? Reactors are the safest source of energy on Earth. Nothing is more safe than light water reactors, except for advanced Gen 4 reactors, right? So it's like we can make reactors even yet safer, and they're already the safest thing. So if we could, I'll leave it with this. We never get on an airplane going, what's the safety record of this model? United never says, oh, it's been 2.5 years since we've had a crash. Qantas is not like, well, we've only had one plane go in the ocean in the last 30 years. Nobody except nuclear beats this safety drum, safety, safety, safety. And then it makes people go, well, why are they always talking about safety? Well, is there something they aren't telling us? It's like, I think this is a diabolical, you know, cul-de-sac that we've been backed into. Everyone's always talking about safety, safety, safety. Well, we're the safest thing on earth by far. So why do we keep talking about safety? We should talk about everything else. Anywho, that's enough for me.
John Warmack, Jim, do you want to weigh in on this?
Okay, John Warmack, a couple of comments with regard to the picture of the Chinese reactor. My suggestion is split the screen and put up what the Russians are doing with their BN series reactor to go along with the other reactor. And the Russian program is to become the dominant energy supplier for their satellite countries, and that will allow them to, the country of Russia, to continue to have influence in the rest of the world. So as we sit and do nothing, China and Russia both are actively pursuing advanced reactors. So just a suggestion on that slide. The second big component that I would suggest is this group does not need to have a one and done conference. We need to get back together, unify our plan of attack, and figure out how we move forward, because we will not be able to do it with only the group of people that are here. Let me offer a couple of ideas to you. These are things that I am pursuing, but for COVID, it would have already been done. Big picture, the responsibility of spent fuel is with the people who made it. So if you own a nuclear power plant, you have the ultimate financial responsibility to pay to get rid of it. It is not, I'm going to repeat, not a United States government responsibility. The United States government is responsible for the infrastructure to do it, but the financial responsibility is clearly stated in the Nuclear Waste Policy Act with amendments, which means that there can be a clawback provision to say, hey, by the way, the guys at Callaway, you owe us an extra $20 billion. There was the DC Circuit Court of Appeals case where the Association of Utility Regulators filed suit about having to continue to pay the $25 per megawatt hour, excuse me, the dollar per megawatt hour into the spent fuel trust fund because of a breach of contract. The court specifically said, we are not addressing the contract, we're addressing the law as it was written, and I'll spare you all the detail, but they ordered the Department of Energy to submit a zero cost to Congress, which Congress approved. But that was an interim solution. The cost is still there. So one of the things that I did is I got the Attorney General of the state of Texas to file a lawsuit. It's a very interesting story. It started with Governor Rick Perry, where he was going to sue the department, the Secretary of Energy. And by the time we got the lawsuit going, Rick Perry went from governor to Secretary of Energy. So Ken Paxton wound up suing the guy that started his own lawsuit. It's the most weird legal thing you can ever imagine. And then I'm in the middle of both of that. And I said, Ken Paxton missed the boat entirely on what should have been accomplished. The point I'm trying to make is, if we point out how the law is today, we reopen that issue, you're going to a lot of governmental affairs people wanting to put pressure on Congress, and this can force the issue. Item number 2 of why the Missouri Public Service Commission needs to take care of their fiduciary obligation is we have a lot of reactors that are starting to come online in a few years. They will contribute to the spent fuel problem, and yet they're not making any contribution to the spent fuel trust fund. We need to go back, reopen that DC Court of Appeals interim judgment, interim verdict, that opinion, and then exclude those. So if we've already paid in, we've got it. Otherwise, they have to pay their fair share. And when that happens, we will get the political support to make a change in the direction of the country. That's item number one. The second thing is the National Academy of Sciences did a detailed report about extracting rare earths out of spent fuel. It's economically feasible. So Jim Kennedy and his bunch could wind up in Missouri if that's where the project went. These are thousands of jobs. These are high-paying jobs, and it would be an advancement for our national security. It will clean up the environment. It will give us rare earths that we currently don't have accessible, but we have to get our coalition built with like-minded people to make it happen in Congress.
We are unfortunately out of time. I'm going to have to cut it off there. Rich?
Okay, first I want to do some thank yous. I want to thank the panelists for the excellent discussions we've had. I also want to thank Angela for doing all the work of setting this up. And in particular, I want to thank Melanie Keeney, who's been behind the scenes making this all happen. It's taken a lot of hard work and it's come together really well. We're not ending, we're just downsizing. The next session will be open only to US citizens that have registered for that session. And so we'll take a pause while Melanie gets the right people online and the right people offline. If you are either a non-citizen or you have not registered, it would be simpler if you could just drop off the call. So again, for those of you that are leaving, thank you very much.
Excuse me, can I say, I'm sorry, can I just say one quick thing before we go?
Sure.
Actually, two quick things. First thing I wanted to mention was with regard to what I said earlier about training. I just wanted to quickly say that my organization, the Engineer Research and Development Center, is not in the business of deciding training. That was just me saying what I, as a subject matter expert, think. Specifically, though, the organization that handles that is TRADOC. It's a 4-star organization, training and doctrine. Just wanted to clarify that. I'm not the decision maker on that. I just give my 2 cents. The other thing I wanted to quick mention is for those of you who are unable to join, there is a portion of my presentation which is already available online and for free. It's not behind anything. If you search Project Pele, Jeff Waxman, W-A-K-S-M-A-N, some of my slides are the same as his. So although I can't tell you necessarily everything, you can see some of the exact same slides that I'm going to be briefing. And that's all. Thank you.
Thank you very much. So again, we'll take about 5 minutes to reconfigure ourselves and see you then. Thank you.